Thank you. Thanks for the introduction. I'm Ozzy. I'm the Principal Product Manager with the Math Libraries team. And today with my colleague from the engineering team, Babak, we are here to present some of the recent work that we have done in the math libraries in enabling Blackwell platforms. Very quick on the agenda. Again, the reason that we are here is introduction of Blackwell platforms, and we're gonna go across many libraries and highlight some of the key features of Blackwell systems and bring examples of how these libraries across many different applications deliver performance on these features. But before that, why math libraries? Why using math libraries? First and foremost, because they bring ease of use to our customers. Without libraries, our users need to have in-depth knowledge of hardware to be able to do programming with CUDA. And libraries provide an easy way to program on GPUs. In addition to that, they also provide a best performance because we have a whole group of people across many layers of the software stack tuning these libraries for best performance. But two key aspects that I want to highlight today mainly is on hardware portability, especially in light of introduction of Blackwell, which this conversation is tied to, and also support for a wide range of functionalities. One of the key values of libraries is that once these new hardwares are introduced, upon their introduction, libraries have it in their roadmap and a strategy to support them day one, as I will be showing multiple examples through this presentation. This truly eliminates a lot of pain from our customers for migrating their code from the old platform to the new platform, and thus accelerate time to market for our users. And also, we provide a whole set of different libraries and functionalities that support many different applications. And again, there are numerous examples that I try to show that in this presentation. An overview of math libraries. First and foremost, math libraries fall under the category of CUDA X libraries. We have about 400 or more libraries, and it's really, I don't think any talk can go through those lists extensively. Even here, I'm not trying to cover the math libraries. All I want to show is that we have a whole core set of libraries which are mainly on primitives and solvers across dense and sparse operations, and some other libraries like QFFT, QRAND. And on top of that, we have a set of libraries which are extension libraries. They provide additional functionality or interfaces to these libraries, including Pythonic interfaces, or, for example, having multi-GPU, multi-node support through the MP libraries. The ones that I have shown with green are the ones that we will cover in this presentation with some examples. Now, going to Blackwell Before going into the libraries, because we will be comparing the performance of libraries across some Blackwell platforms and sometimes compare them to Hopper, I thought we condition the conversation by highlighting two system configurations that I will be referring to in this talk. One is GB200 NVL72. This was also highlighted in the keynote yesterday. And the other one, DGX B200 NVL8. At a system level, these two are different. One, in terms of host, in GB200 system, we use Grace as the host, which is different from DGX system where we use x86 CPUs. And the other component, which is really I want to highlight before further diving into this conversation, is the NVL72 link. This is a pool of 72 GPUs that are connected through high bandwidth NVL link. And it's different from DGX system in that in those systems, only 8 GPUs are connected through NVL, and the rest of the nodes are connected through InfiniBand. This is something we're gonna come back in subsequent slides. Also, in many cases, we will be benchmarking against Hopper, whether H100 or 200. Mainly the system that we will be benchmarking is DGX, sometimes HGX. These are similar to DGX V200 with the difference of, obviously, the chip. Again, 8 GPUs connected through NVL link and x86 CPUs. At a hardware level, highlighted again yesterday, there has been a whole set of hardware new features which were introduced. From a compute perspective, we have introduced FP4 in Blackwell systems. And another key factor to consider is that we continue to support FP64 and FP32, but the rate of increase of these two numerics on the hardware is not similar to what we have seen in the past. And as a result of that, libraries are now opted for emulation, and we will be showing through this presentation how emulation can be a really powerful technique in delivering performance for these precisions. Memory and memory bandwidth, these are trends that are predominantly being encouraged by the large size of LLM. Training and serving definitely higher memory capacity and also memory bandwidth. The ratios that you see here for memory bandwidth are B200 compared to H100 or H200. So those two values would be either the ratio of B200 to H100 or B200 to H200. And then on the right side of the picture, you see two other features I have highlighted. One is the having Grace as a host. Although I highlight Grace is not new to Blackwell, Grace also was introduced in Hopper system. And the other feature is introduction of a decompression engine, which is going to be used for data decompression. And we will be showing how different libraries would be supporting each of these features. Now, with that, I pass it to Babak to cover emulation and numerics through cuBLAS.
Thank you. So why would we think about emulation? If you ever wondered what else we can do with the growing throughput of AI precisions, like tensor cores, then you're not alone. Emulation is one of the things that we've been thinking about, how to leverage the higher efficiency and higher throughput tensor cores to emulate matrix multiplications of higher precisions like FP32 and FP64. There are two ratios highlighted here. You've probably seen various versions of this chart, but yellow bars are basically Blackwell throughputs. You can see, for example, that a tensor core has more than 100 times throughput of FP64 today, and BF16, for example, has about 28 times more throughput than FP32. The choice of these ratios are not actually is not arbitrary. It turns out that we can use these tensor cores at higher throughput to emulate these higher precision matrix multiplications. So what we want to do basically is to make sure that you can tap into the higher perf over watt efficiency of these chips, and also if we can expose this in the libraries in a way that is not intrusive to the users, but still we want to provide enough control for expert users. So there was actually a deep dive session yesterday by Samuel Rodriguez on emulation methods. So we're not going to go very deep into these, but you have the session and some QR codes for papers. You can take a look at those. But in a nutshell, FP32 can be emulated with BF16 tensor cores. We can actually have 9 inner matmuls or sub-matmuls or partial matmuls in BF16, and then we can sum them up to represent an FP32 matmul. FP64 can be today emulated with int8 tensor cores. It's a little more involved than FP32 emulation in that it has a degree of freedom that controls its accuracy and it's data dependent. And we've been basically testing these and implementing these in the libraries. I'm going to show you just a few of the highlights of performance in matmuls and in end-to-end benchmarks real quick. If you look at how we're emulating FP32 in cuBLAs on Blackwell B200, you can see, for example, by looking at the solid line with diamonds, that we consistently have speed up above the matrix sizes of 512. These are score matrices for now. These plots look a lot like roofline charts. So they increase and saturate the bandwidths with the size, and then they saturate peak performance. You can see that we can reach up to 3 times the native FP32 throughput that's on Blackwell today for B200 and 4x over Hopper. For FP64, we have relatively a similar picture. We can see that with FP64 emulation using tensor cores, we can achieve a 2.8 speed up factor over the native FP64 throughput that's on Blackwell today, and that is about 1.5x of a speed up on H200 Hopper. You will notice something here in the title that is called S equals 7 or 56 bits. This is the degree of freedom that I talked to you about earlier. This controls how many bits of accuracy you retain through the emulation. You can have more or less by this S parameter, and that basically defines how many sub-matmuls you need to do to achieve that bit count of accuracy. This is not the end for matmuls. We've been testing this on actually end-to-end applications as well. On the left side, you have EC trans, which is an operation that happens a lot in weather simulations. It transfers from spherical coordinates to the frequency domain and back. It used a lot in weather and climate simulations. You can see that the part noted here as SGEM is accelerated by 2.4x with the FP32 emulation, and end-to-end, the application was sped up by 1.4x. Similar levels of power efficiency was achieved. On FP64, we've been focusing on several other applications, and one of them here is Berkeley GW, which is basically a material simulator. Here we used an emulation accuracy that's equivalent to 56 bits versus native FP64. Again, you can see the part that it is subject to emulation and speed up due to emulation sees a speed up of about 2.1x with the end-to-end application speed up of 1.8x. We're working a lot on testing accuracies. So in all of these cases, accuracy is on par with the FP64 or FP32 native precision. And it's also not just cuBLAs, libraries, other libraries like cuSolver, in this particular case, cuSolver DN, is trying to test and enable these emulation modes. Here you can see a compute-bound, compute-intensive operation, the QR factorization in cuSolver DN that is leveraging FP32, and it can reach up to 2.3x. LU is very similar. And we are going to basically expose this in cuSolver DN, cuSolver MP, and then FP64 will be next. Now, let's go back to AI matmuls. We talked about scientific computing matmuls, and so back to cuBLAS supporting reduced precision matmuls. So if you use Hopper and the FP8 format for training or inference, you know that this was introduced hardware with Hopper. It supports one scaling factor for an entire tensor or matrix. Blackwell extends this to enable more granularity. You can have both FP8 and FP4 with block scaling now on Blackwell, where sub-blocks of these matrices will share a scaling factor. You can actually see this little cartoon on the right, thanks to our NV Math Python colleagues who basically are showing every 32 element block of this matrix has one unique scaling factor or color here. This diagram shows how a general matrix multiplication is done using these cores and the scalings. You can see the A and B inputs, the scaling factors coming in, and several other operations along the way. That's very typical in matrix multiplication. And then you can recover also the scaling factor of the output at the end more efficiently. What block scaling allows you to do is more control on granularity of applying the scaling to these narrower and narrower data types, which should give you more degree of freedom in experimenting in training and inference. How are we doing on Blackwell with matmuls of the established precisions like BF16, FP8, and then the new block scaling formats? So if you look on the left half of the chart, you see the compute-bound matmuls speed up. We are basically reaching close to what the hardware specs on B200 and GB200 guarantee, and so you can see something like 2x for BF16 or FP8, and a lot more than that with FP4. Here, Hopper FP8 was chosen as the baseline for block scale formats. And on the right half, you can see that because we want to present the library performance as a general, we took basically about 1,000 random sizes, very small, medium size, large. And you can see that speedups are a little lower just because you have a lot more bandwidth bound problems and you can't reach the peak with all of them. But you can see that speedups are sustained, and we optimize basically the kernel implementations in the library and the runtime heuristics that chooses kernels at runtime for Blackwell. And how are we doing on actual matmuls that participate in important LLM training and inference workloads? Here I grouped into LLM training and LLM inference. These come from a variety of models, important models these days, Llama 3.1, et cetera, LLM training, you can see that the matmuls in these models are accelerated by about 2x, either FP8 or BF16. And same numbers repeat for the inference sizes as well. These are just for the matmul part of these models. So your final speed up depends on other things that are in these models usually. And yeah, with that, this is a summary of matmuls.
Thank you.
Thank you.
Thanks, Babak. This is working. Great. So Babak covered FP4, also high precision numerics, and with that, basically provided a summary of compute-intense operations and how two of our math libraries with the example of cuBLAS and cuSolver are supporting these operations and delivering performance. With that, I'm actually going to move to two other libraries, cuSparse and cuFFT, and focus more on memory bandwidth constraint type of problems. Starting with cuSparse. cuSparse is a CUDA-accelerated, GPU-accelerated library for sparse operations. Those would be matrix multiplication, matrix vector multiplication, and vector-vector multiplication. Many of you may already know that these operations are typically memory bandwidth constrained. And in this case, we have shown with cuSparse on Blackwell across a whole set of benchmarks, we could deliver something in the range of 1.4, 1.5, in some cases even up to 2.4 speed up compared to Hopper. These results are obtained comparing B200 versus H100. And I provided the nominal hardware ratio for bandwidth, which is around 2.4. The beauty of these slides is that this slide actually is that it shows cuSparse, one of our libraries, by enabling and taking advantage of this memory bandwidth addition, now delivers performance which are relative to hardware nominal ratio. I have examples from SPMM, SPMV, and I want to put this disclaimer that obviously these results vary depending on the data type, on the matrix layout, on the sparsity format. And we provided a whole range of results for different varying input parameters. Now moving to QFFT. Fast Fourier transform operations are again the type of operations which are memory bandwidth constrained. In this case, QFFT, a library, a GPU-accelerated library for fast Fourier transform, is enabled on Blackwell, and they have made comparisons with Hopper system with H200. These operations are memory bandwidth. The ratio of B200 to H200 nominally from the hardware perspective is 1.7. And here on this graph, you can see that for a whole range of FFT sizes, these are 2D FFTs, QFFT consistently gets close, very close to actually the nominal ratio to 1.7. With that, I want to cover QFFT MP. If scaling across multiple node and multiple GPU is something that your workload requires, I think this slide is for you. And this is one of my favorites in this presentation. So QFFT MP is a MGMN library, multi-GPU, multi-node. These are a whole set of libraries that we have developed for our users for scalability across GPUs. And these are the type of problems that communication has a lot of overhead. And the goal of these libraries is to hide or make the communication overhead as little as possible. This is an example of a 1023 to the power of 3 FFT example. The input to this problem is fixed. The difference in the chart, let's take the solid green chart first, and I will walk you through the rest of the charts, is that in this case, we are dividing the example to 1, 2, 4, up to 64 GPUs. And this is typically called strong scaling. The purpose of strong scaling is that your input is the same. You just throw more GPUs into the system with the hope of reducing the time to solution or solution time. The green solid line shows the result of a strong scaling for this FFT example across 64 GPU nodes, and you see here excellent linear scaling. This is an example which has run on GB200 NVL72. Going back to the initial slide, NVL72 systems are systems that 72 GPUs are connected through NVLink. These are high-speed connection, and as a result of that, the whole overhead is almost cannot be seen here. You see a perfect linear curve. Now, going to the dashed magenta curve. This is the same example, but run on B200 NVL8. These are systems where only 8 GPUs within the node are connected through NVL. Past that, between the nodes, the connection is through InfiniBand. And this is perfectly observable here. The inflection point, the point that you see now that the magenta curve starts breaking and going up, is where InfiniBand comes into play. And past this point, the effective bandwidth of the entire system is a combination of InfiniBand and NVL, but mainly controlled by InfiniBand. As a result of that, you see that there is a bump, and therefore the overall performance of the system decreases. And if, for example, you target a time like 2.35, on NVL72, you can get to the result with 8 GPUs. But for a DGX system, which only 8 GPUs are connected through NVLink, then you now require 64 GPUs, a factor of 8, which is really substantial. I'm going to move to the next curve here, the gray dash curve. That's the curve for the same input example, now run on DGX H100. These are very similar. DGX H100 and DGX B200 are very similar in terms of NVLink 8 GPU configuration, NVLink domain size, and also InfiniBand bandwidth. Therefore, the initial response, as you can see, is very similar. And then again, at the 8-point GPU, you see the inflection point, and then the two curves start getting very close to each other because now everything is controlled mainly by InfiniBand bandwidth. There is one minor point that I want to also make here. If you remember from the previous slide, we said on a chip-to-chip level, there is a ratio of, I think, about 1.6, 1.7 between H200 and B200. If you look at the first two nodes on this graph, compare the 19.62 on the gray graph, which is coming from Hopper, to the first point from the B200 system, you get exactly that ratio. That comparison, basically the distance, the vertical distance between the gray curve and the B200 curves is coming from the chip memory bandwidth, the ratio between the memory bandwidth of Hopper versus Blackwell, something we covered in the previous slide. So the takeaway of this one is that NVL72 scales really perfectly with cuFFT, and we are talking about 8-time reduction in number of GPUs if you're scaling beyond 8 nodes. One last highlight of this slide is that now if you really have a low SLO, for example, you want to get to very fast solution time, 0.72, I take it as an example here. In this case, with NVL72 systems, you can get to solution with about 32 GPUs, but no matter how many GPUs you throw into DGX system, you will not get a response. As you can see, these curves start to plateau, and this plateauing is the direct effect of huge overhead of communication, that at that point, breaking the system into GPUs no more makes sense. Okay, we're going to transition to cuDSS. cuDSS stands for CUDA Direct Sparse Solver. This is one of our more recent libraries. It's a GPU-accelerated libraries for a sparse direct solver, and it already has seen a lot of traction in the industry. I want to emphasize this is a GPU library still, but the beauty of cuDSS is that it actually exercises a heterogeneous system paradigm in that it uses host and device, both of them smartly whenever it sees a fit. And in this set of slides, we're going to focus on Grace and how cuDSS smartly uses Grace. Going back to the introduction of Grace, Grace was introduced in Hopper system, but it's also available in GB systems. And the beauty of Grace is the high bandwidth interconnect, C2C interconnect between the CPU and the GPU. And that makes a huge difference when compared to x86 systems. As a result of that, Grace provides a really unique opportunity for a shared memory type of exercise. And cuDSS takes advantage of that. cuDSS has a hybrid memory mode, and in addition to the hybrid memory mode, also it has a hybrid execution mode where it offloads some of the computation to CPU when it sees a fit. Starting with the hybrid memory mode, this is the result of cuDSS running on hybrid memory using Grace memory as a shared memory pool. These results show the comparison of cuDSS versus cuDSS. In one case, cuDSS has run on GB systems using Grace as the memory, and in the other case, they have run on x86 system. In both cases, the chip is Blackwell, so it's a fair comparison. The only difference between these two systems is the CPU and the interconnect between the GPU and CPU. And you can see that on average, we have a 2.1 factor speed up for factorization and 2.5 for solve. Very quickly, moving to hybrid execution. Again, cuDSS smartly offloads some of its operation when it sees a fit. For example, something that is highly sequential, or when these matrices in this case are very small and they don't exhaust the GPU to the host. So in contrast to the previous chart, which were mainly, the benefits are mainly seen in larger matrices, this is example that the benefits are mainly for smaller matrices, CUDA offloads, execution, solve, and factorization. By execution, I mean of smaller matrices to the host, and as a result of that, it delivers something close to 1.8 average speed up. And I want to highlight that with these two slides, I just don't want to mention CUDA as an example, but more of our library attempt to basically exhaust every possible opportunity to deliver performance. Now moving to image and data compression libraries. Blackwell has a new feature, which is a hardware decompression engine. This is something that is less highlighted. And we have a library, NVComp, which is for data compression and decompression. In this case, NVComp has enabled or leveraged the hardware decompression engine, which was introduced in Blackwell. And we have shown that using NVComp, you can get significant speed up with the hardware feature. So these results are, again, comparison of NVComp on Blackwell to make a fair comparison. In one case, it's only the software mode, and in the other case, NVComp leveraged the hardware decompression engine. And NVComp supports many different algorithms. There has been connect with experts, and I think there has been technical talks on this library as well. You can connect with the team. 9x, 4.4x, 5x speed up using the hardware decompression engine. Very similarly, Blackwell has a JPEG engine. If I'm not wrong, JPEG engine actually has been introduced in Hopper. It's not new to Blackwell, but NVJPEG, another math library, is enabling this feature, and it delivers significant performance, whether it's used on software mode or when it's compared to software using the hardware feature as well. For this case also, we brought the example of comparison with Hopper. Compared to Hopper, you see 1.3 speed up for the decode phase. So basically, that's a summary of my talk. I know I only have 6 minutes left for questions and answers, so I'll go back to the story that we were trying to tell here, how math libraries can help you with your applications. Blackwell has a lot of new features. In terms of the low precision, we have FP4, and we have now block scale support for FP4 and FP8. Having block scaling enables users to have more granularity control over scaling, and this helps with the accuracy. This is a feature that is now enabled. In terms of applications that require high precision, FP64, FP32, we have shown consistently through our libraries that with emulation, we can deliver significant speed up compared to Hopper. For FP32, this can be as high as 4x, and for FP64, this can be about 1.5. Memory bandwidth, we have huge memory bandwidth increase in Blackwell, and our libraries that are for problems that are memory bandwidth are delivering on that very close to the nominal ratios. And another key highlight, NVL72, this is a system which is exceptionally well for scaling. With some libraries like cuFFT-MP, we have shown excellent linear scaling, which resulted in about 8x reduction by ratio in the number of GPU counts. Grace is an asset. Its high bandwidth connection to GPU provide an opportunity for using its memory for problems that are large, and CUDA has delivered on that with an average of 2 to 2.5 speed up. Also, we use that for heterogeneous or hybrid GPU, CPU execution. And finally, decompression engine is now new in Blackwell, and our NVComp libraries support that. And the overall message of this talk is that our libraries are supporting a whole range of applications across many different industries. We are not just focusing on one. We support AI, as Babak pointed out, through cuBLAS and low precision. We support high performance computing, engineering, and scientific application. And Blackwell is actually a platform that can deliver on all of these. Thank you. I think we have about 3 and 4 minutes for questions. Yes. No, you go.
Thanks for the nice presentation. So my question concerns cuSolver MP, the MPI distributed version of cuSolver. So in previous years, since there's only been a small amount of large machines, Cray slingshot machines with NVIDIA GPUs, there wasn't the business case for NVIDIA to get cuSolver MP to work well in slingshot. Now that there are newer large Cray EX machines coming online with NVIDIA GPUs, such as the Bristow Isambard machine and then Alps at CSCS, is there now a business case for NVIDIA to invest in getting cuSolver MP to work well on Cray slingshot machines, or is there still insufficient business case?
I'm missing the point about the machines. Are you generally asking is there enough business case for cuSolver MP or cuSolver MP?
Because previously cuSolver MP hasn't performed well on Cray slingshot, so it's been optimized, of course, for InfiniBand machines. But I know in the past, when I like a year or two ago, when I've talked to people at NVIDIA, they said that naturally with a small amount of supercomputers with Cray EX, there wasn't sufficient business case to optimize cuSolver MP for slingshot, and I'm wondering if that's changed with the newer large Cray EX machines with NVIDIA GPUs.
What I can say is that we are focusing on cuSolver MP. We see huge potential on that, and we are doing investment. Specifically with respect to your point, I wasn't here, and I don't have the background into why there was a message that cuSolver MP wasn't prioritized, but Harun might have some, or Becca also from the product side might have some background into that question.
Oh, sure. Thank you.
Harun, do you want to answer that? Or? Okay. Okay.
Go back to the
Back to fast Fourier transform example.
Yeah, I was just curious because you stopped the curve at 64, which I presume is because that's the NV-link sort of thing. I was just wondering what would happen beyond that, because I suppose the green curve would be plus InfiniBand if you go past 64.
I would say that it would be InfiniBand past 64 as of now.
You were expecting for the performance. I was wondering how
It should be the same. Like you should see once InfiniBand come into play, you should see the same bump.
The same bump and then linear.
Yeah.
Because the purple one you stopped presumably to be the same as the green one, but that looks like it's plateauing earlier. But you just stopped at 64, so I was just curious what you expected, why you stopped at 64.
That I don't have visibility as to why we stopped at 60. That can go on. I don't see any reason.
I think it's converging, so I think it's going to plateau earlier. I was just curious.
No, it's not going to plateau earlier. I can answer this question because this is like really. So in terms of why if the question is the green line we wanted to show, yeah, exactly. So that, I don't know why it is stopped. It might as well, and don't quote me here, it might be availability, but generally I expect the behavior of the magenta and gray to become identical, because basically the effective bandwidth of that system is mainly being controlled by InfiniBand, and as long as InfiniBand between the two of them are the same, they're gonna be the same. And this green curve past 64 GPUs needs to go through InfiniBand. I don't know. I mean, I'm pretty sure there is no system that goes
Yeah,
beyond
I
64.
kind of have a similar question, right? So here, right, why 64 is because these 64 GPU are in the same NVLink, right? You know, same rack. That is NV72. So it's like treated as one domain. It's like a memory is kind of global memory shared. So my question actually regarding to the B200, right? So in the B200, so this once it exceed the one rack, you know, like boundary, right? So here it's 8, it's one node, right? So it's like, it's flat. The performance is close to H200. So it's kind of, you know, is IB bounded. So once get to that point, it's highly, you know, very difficult to scale up in this case. So for example, with multiple node, we see kind of a flat, right? So what is advantage on the B200 in this case? Because for NVLink like 72, right? So for the Grace platform, once it exceeds 72, right, that boundary, well, it sees the same behavior. So same thing, like IB bounded.
I'm not sure if I get the question completely, but I will, if the, and please correct me, we can have this conversation after the talk. If again, the question is why those two start to behaving very similarly, although one of them is so one of them is Blackwell and one of them is Hopper, the answer is that because this is an FFT example, and this example is not controlled by, it's not a flop bound. Therefore, the differences at the chip level of H100 and B100 is less relevant. What is more relevant for this example is memory bandwidth and network bandwidth. And because both of them are DGX systems with similar InfiniBand, once InfiniBand at this point comes to kick in, it dominates the effective bandwidth of the system. And that's why that these two systems start to behave similarly past that point.
Are you saying this is kind of special case, doesn't apply the other cases? So that's also
I'm
one
not
of my
gonna say-
question, right? So it's like...
Is there, right?
I think
yeah.
Miguel behind you
Yeah,
will have some
let's
answers
have
to
other
you.
questions.
Yeah, so I can answer. I think, yeah, I work in QFFT and QFFT MP. So yeah, so the bandwidth is limited by the InfiniBand bandwidth. So once the InfiniBand kicks in, you're going to see the same profile for both cases. And so as you know, as you move to higher number of GPUs, there's a moment where the data, because this is a 1K cube problem, is you're bound by the amount of data that you're exchanging, and so that's when the overhead kicks in, and so that you achieve that stable regime. If you look at a higher, like a larger problem, you'll see the same scalability up until the point where you get to 72 GPUs, in which case InfiniBand will kick in, and you'll see a bump in those cases too. Does that answer the question?
Can we?
Sorry, what?
We have.
Yeah, you see a similar InfiniBand. Yeah, and in 72 and the 128, yeah, you would see an InfiniBand kicked in. Yeah. Yeah, this is yeah. We were.
Everyone, we'll be starting our next session in 15 minutes.